In this video, I'm going to teach you how to solve first-order linear differential equations using the integrating factor method. So integrating factor. Okay, this technique takes a first-order differential equation of the following form: dy by dx plus p of x y equals q of x. So these are just functions of x, okay? And it's called the integrating factor method because we multiply both sides of this differential equation by some integrating factor r of x. Now, I'm going to show you why we do that, but first let's put it in the form. R of x dy by dx plus we have r of x times p of x y is equal to q of x r of x. So we multiply both sides of the differential equation. Now, why do we do that? Well, sort of the hint comes from this. Okay, this r times dy or r times y prime kind of looks like, if you look at the product rule. Okay, I'm going to use r and y in my product rule example here so that we match what we see on this in our differential equation. So dy y times r by dx is equal to, and here we'll say y prime r plus r prime y. What is that? Well, that's dy by dx, or I could say ry prime. Let's make it look the same as that. Okay, so I'll just move this over a little bit. Say r times dy plus dr dx times y. Okay, so we have this guy, this guy, okay, and y is here, but we have this is the difference between the two. Okay, so what are we trying to do? Well, look, if we can convert our differential equation to make it look like the product rule, okay, then what we can do is we can simplify our equation by going, if you remember the integrating combinations, we can replace the right-hand side right here of our equation with dy r by dx. This is easier to integrate. Okay, and our goal is to integrate both sides of our differential equation. Okay, so really what we're going to do in order to make them the same, let me erase this. What I want to force is I want to force this guy, I want to force dr dx to be equal to rx px, or the other way around. Force rx px to be the same as dr dx so that I can sub dr dx in place of rx px. Okay, so px is already determined. It comes from the equation. So only rx can be changed. Right? R of x is that integrating factor. So basically, if we can choose our r of x to be such that rx px equals dr dx, then we can sub in dr dx into our differential equation. And then it will look exactly like the product rule, so we can basically take our differential equation and just make it dyr dx. So we got to choose our r of x. So let's do that. Let's solve. This is going to be our first equation. Okay, the solution to this differential equation right here is going to be our r of x. So we're going to solve this for r of x. So we do that by separating the variables. Multiply both sides by dx. So you'll have dr is equal to, we have rx px dx. Okay, and then divide both sides by r. I'll just leave it as r instead of r of x. So this will go away. And then now we have we've separated the variables, right? R's are on one side, all the functions of x. R's are on one side, p's on the other side. So now we can integrate both sides. Okay, I'll do that here. So what's the integral of 1 over r dr? Well, that's the ln of the magnitude of r plus some constant c, 1. And we don't know px. Px comes from the problem. So I'll just leave that here. I want to show you, I'm going to move the cx to the other side. Okay, so I'm going to make this, so ln of r is integral of px dx plus, okay, we'll call it c naught. Okay, when I move it over, it's going to be negative c1. So what is this? Well, this is e to whatever's on the other side of the equation is equal to magnitude of r. So r is equal to e, the integral of p of x dx plus c naught. Well, look, that's the same thing as e to the integral of px dx times e to the c naught. Well, that's just some constant. I don't know, we'll call it k. How's that? Okay, so look what happened. Because we have that constant k, what this becomes is, so k can be positive or negative, right? X dx. K can be positive or negative, so we don't need the magnitude of r, so this is r. And the other thing is, look, so k can be positive or negative, so that takes care of that issue. But we're going to multiply both sides of our differential equation by r of x. So we can divide the k out from both sides. So if we divide k, both sides of the equation by k, we can actually eliminate, we don't need k. It will actually divide out from both sides. So really what's necessary here is integral of px dx. And in fact, yes, this integral is indefinite. There will be a constant of integration that will be introduced by this integral, but the same thing will happen from this integral. It'll give you a constant, but it will multiply the same way we saw here, and then you can divide from both sides. So really, when you do this integral, you can ignore the constant of integration that is introduced. So at the end of the day, look, we now have, this is the first equation. This is equation number 1, which is the solution. So look, we can call it 2, or we can call it whatever we want. We can say this is basically the solution to the differential equation here. Okay, we'll call this 1 star. Okay. All right, so look, as soon as we do that, as soon as we choose our integrating factor that we multiply both sides of the equation by, as soon as we choose it in this way, now this rxpx, okay, from our differential equation, it now can be replaced by dr dx. So we can go in, I'm going to go back up here and rewrite our original equation. Just drop it down like that, below this. Okay, let's bring this down here. So our original equation, we go here, it's rx dy dx. All right. Plus, set rx px times y equals q of x r of x, right? And we said that when we choose r in this way, we can change this differential equation to rx dy dx plus, now this is dr dx times y equals q of x r of x. But look, this right here is the product rule that we have up here. R dy dx plus dr dx times y is dyr dx. So we're using our integrating combinations understanding to simplify our original differential equation so that it's dy r dx is qx rx. Okay? And we can separate the variables really easily just by multiplying. Like you can use this as your as a formula if you like. Okay? And this will remind you that what happened was that you simplified using the integrating combinations, okay, by forcing rxpx to be equal to dr dx, okay, by choosing r using equation 1, okay, you've simplified your differential equation to this form. You can call this your equation 2, or we can call it 2 star, because you can actually solve for y directly from this equation, right? So multiply both sides of the equation by dx, so then you get dy r is qx rx dx. Okay, then integrate both sides. Okay, well, the integral of dyr, this is like z, right? dz. Yr, let yr be z, and so the integral of dz is z, so, well, it's z plus c. So really it's just yr plus some constant is equal to integral of qx rx dx. So the r came from p, right? R came from p, and q is also part of your problem. Okay, so these both, the whole right-hand side comes from the problem itself. All right, so what you could do is, you see, what we could do is we could take this guy, bring him over to the other side of the equation, and then we have yr, okay, equals integral qx rx dx. You could add this constant, okay, but look, this is an indefinite integral. It's going to generate a constant as well, so you don't really need this constant as part of your formula, okay, because this guy is going to generate a constant because it's an indefinite integral. Okay, so we can leave it like this actually, or you could just divide both sides by r, and you'll get your equation. Okay, if you do it like this, you get your equation. So this is 2 star. Okay, this is 2. So what do we have? We have really 2 equations. Okay, 1 star so the solution to this differential equation, which we forced to 1 star, is equation number 1. And the solution to our differential equation that we want to solve, the original one, is you could use 2 star, or you can go straight to the solution for y. Okay, that's another. All right, so now, what does that mean? Well, that means that what we could do is we can simply look at our equation, okay, of this form, dy dx px qx. We can get r from p, okay, we get r from p right here, and then sub that directly into either 2 star or 2. Q, so r comes from p, which is the problem. Q gets used in equation 2, and you get uniquely the solution for y. Okay, so that is our differential equation. Okay, and so now what we're going to do, or this is the how it was we derive the formulas that we use. Now we're going to use these formulas to solve problems. Okay, so let's take a look at some examples. All right, so let me go here. First thing I want to do is I want to remove everything from here. So select all and delete. Actually, I have to go here, Control A, and then delete everything. Okay, I'm gonna clear my thing. Okay, so now let's look at some examples that use the integrating factor method. All right, so the first example is going to be x dy minus 3y dx equals x to the 3 dx. Okay. So this is our first example. And what we need to do is we need to convert this into a form that looks like, remember, it is dy dx plus pxy equals qx. Okay. So we have to do that first. So if we divided this by x dx, both sides by x dx, what we get is this cancels. Okay, this cancels. This guy cancels. This one becomes 2. That cancels out. So what you get is you get dy by dx, right, minus 3 over x times y equals x squared. So we know that this guy is p of x, this guy is q of x. And the way we solve, we said, was we need the integrating factor that would allow us to convert the left-hand side of our equation into the product rule, right? To equate dr by dx times with p times r. Okay, so if we were to multiply, so r of x is equal to e to the integral of px dx. And what's that? Well, px, e to the integral, we're going to say negative 3, 1 over x dx, which is e to the negative 3. We have the ln x plus c, but we're going to ignore the constants. Ln x, okay? And what we know is that a ln b is equal to ln of b to the a. So here a is negative 1, or negative 3. So this guy is e, okay, to the ln negative x to the negative 3. Okay, so that is what we have. We also know, look at this, e to something. So this little e to box is equal to x to the negative 3. Well, this e is to the same box. Therefore, this equals magnitude of x to the negative 3. Now, one thing I failed to tell you, you see, this guy right here, there would be a plus c, and what that results is a constant here. This constant can be positive or negative. So because of that, r of x, we don't need to take the absolute value anymore. Okay? Because the constant can be positive or negative. Okay. So we know what we're going to multiply our equation by. This r of x becomes x to the negative 3. And then we said, okay, we can jump straight to the solution. And I'm going to use the solution equation. So it was y equals 1 over r, or r of x, the integral q of x, r of x dx. Q comes from the problem. Q, we see, is x squared. So what do we have? We have that y equals 1. Now, r of x is x to the negative 3. So this becomes just simply x to the 3. And then this becomes, okay, q of x is now x squared. R of x is x to the negative 3. So we're going to take the integral of that dx. Okay, so this becomes x to the 3 times the integral of 1 over x, really, right? So 1 over x dx. Now, what is the integral of 1 over x? Well, it's ln x, so we have x to the 3. Here we have ln magnitude of x plus, it's an indefinite integral, so plus some constant. Now we have to consider this constant because we're not dividing both sides by anything. So what I have is y is x to the 3 times ln x plus c. Or another way of putting it would be x to the 3 ln x plus c x to the 3. Okay, so this is a solution to this differential equation. Okay. Let's now take a look at another example. So I'm going to click on delete everything from here, Control A, and then delete that. Okay, let's take a look at another example. We'll call this example B. Okay, so we're going to say that y prime plus cotan x times y equals cosecant x. Now, cotan, okay, is 1 over tan, right? Cot x is 1 over tan. Okay, so that means that if tan is sine over cos, then cot is cos over sine. Okay, and cosecant, CSC, is 1 over sine. Okay, all right. So cotan is 1 over tan, cosecant is 1 over sine. All right, so let's keep these. The reason why we're going to do this, why I need this, is because, look, this guy is p of x. We're going to do an integral of this guy. So unless you have a table of integrals, that's kind of difficult. This guy's going to be q of x. Okay. So we need r, right? R of x is e to the integral of px dx. So I need this integral of px dx first. So what's the integral of p of x dx? Well, p of x is cotan, but I'm going to go use the integral of cos x over sine x dx. That's easier, unless you have a table of integrals, it's easier to do it this way. Why? Because the numerator looks to be related to the derivative of the denominator. So we can use u substitution here. So we could say let u be sine x, right? Then du by dx, derivative of sine is cos, right? It's cos x. Multiply both sides by dx, so du is cos x dx. So look, cos x dx we have in the numerator. Sine x we have in the denominator. So we can do a direct substitution into our integral here. So that is just cos x dx is du. It's this du. And sine x, or well, 1 over sine x is 1 over u. Okay, so what we have here is the result is ln magnitude of u, right, plus some constant. Now, we can ignore this constant. Remember, we said that this is just going to become multiplied. It's going to be a constant in Rx that you can divide both sides. So I'm gonna get rid of the c. I'm going to ignore that. So the integral pe to the px dx is just ln of sine x. Okay, but r of x is e to the exponent. So r of x then becomes, it's e to the exponent of px dx, which is e to the ln, remember it's base e, of sine x. So this e, so this whole expression, ln of sine x equals something, right? Equals box. E to box is sine x. E to the same box must therefore be magnitude of sine x. Now, one thing that I should note here, remember, we threw away this constant. Well, this constant would basically put a multiplier k, okay, some unknown coefficient k, which can be positive or negative, okay? So this would have been a k times sine x, right, rx. Okay, but k can be positive or negative. So we don't need to take the magnitude of sine x. Rx, if we divide by the magnitude of k instead, will then simply be sine of x. Okay, that's all we need to do. Okay, so Rx is sine x. Now that we have that, we can sub Rx and Qx into our solution equation. And what's our solution equation? Well, it's very simply y is equal to 1 over r integral qx, or x, I should be consistent here, dx. So what is it? Well, it's 1 over sine of x times the integral. Now qx is cosecant x, which is 1 over sine x. Rx is sine x. So we have sine x times 1 over sine x dx. So this cancels. So it's just the integral of dx. Well, what's that? Well, that's simply, okay, keep the 1 over sine x here. It's just x plus c. Okay, so if you want to group it together, you can leave it like that, or you can say y sine x is equal to x plus c. And that is your solution to the differential equation. Okay, let's take a look at another example. So let's clear out our table here. Okay, and let's take a look at the next equation. So what we want to solve here in this example, example C, is y prime plus, now here's what we're going to have. Let me clean this up a little bit. It's going to be is 1 minus 2x over x squared, okay, times y equals 1. So remember, this is qx, this is px. So in order to solve this, we need r of x. R of x equals e to the integral of p of x dx. Okay, so that our solution is going to be 1 over r qx rx dx. Okay, so what we need is we need the integral of px dx. Okay, that's what we need here. So that's the first thing we need to. So the integral of px dx is given by the following integral. It's 1 minus 2x over x squared, okay, dx. Now, we're fortunate that the numerator looks like the derivative of the denominator. So if we were to choose, if we were to say, we're going to use u substitution. So let, right, u equal, okay, well, we could do that. Actually, here, let's do this first. Let's make this equation a little bit, we'll separate it out into two parts. Okay, this becomes the integral of 1 over x squared, which is just x to the negative 2 dx, minus the integral, minus, let's say, 2 Let's leave the 2 inside because actually that's going to be nicer. So minus 2x over x squared dx. Okay? So this separates it out nicely. So let's do that. So what's the integral of x to the negative 2? Well, let's do this. It becomes x to the negative 2 plus 1 over negative 2, sorry, negative 2 plus 1. Plus, it's an indefinite integral, so we need to add constant. And then subtract this integral. Becomes, let's see. Let's cancel this guy out with this guy. I'm going to leave the 2 here. I have 1 over x dx. I thought I would do a u substitution here, but I don't actually need to do that. You could, but it'll be the same. So 1 over x. This is just minus 2 magnitude ln x plus c. So minus 2. We can go like this. Ln of x plus c 2. Now we have another constant. So I could grab these constants and collect them. I know there's a negative 2. I can group them into a single group them into a single constant. So what do I have? I have x to the negative 1, negative, right? And minus 2 ln x plus, now I'm going to just group everything into a single constant like this. Okay, so that's that. Let me go here. Let me just simplify this a little bit more. It was negative x to the negative 1 plus ln of x to the negative 2. Okay, and this is going to be a constant in, so this constant is going to be, so this is e to the px. Okay, let's just leave it for a second. I'll show you what I mean. This is, sorry, this negative 2 is, so a ln b is equal to ln b to the a. Okay, so that's what, a here is negative 2. Okay, let's go and see what we have here. So let's move this up. All right, so what do we have? We have, this is the integral of px dx. So r of x is equal to the e to the integral of px dx, which is, okay, becomes, let's see here. So it's e to the negative x to the negative 1 plus ln x to the negative 2 plus some constant c naught, which we're going to eventually get rid of. So let's keep going. So it becomes e to the negative x to the negative 1. Okay, right? Times e to the ln x to the negative 2 times e to some constant c. Now remember this one, we did this one before. This equals box, so this e to this box, same as this e to this box. So this becomes e to the negative x, negative 1 times ln, oh sorry, not ln, just this guy, just x to the negative 2 times, we can say magnitude x to the negative 2 for now. And then this is going to be some constant. I'll just call it k. Okay, and this is r of x. Remember, because k can be positive or negative, we don't need this magnitude anymore. Okay, k allows things to be positive or negative, so we'll just say x to the negative 2. Okay, so that is our r of x. So r of x, and I can remove this k. I can divide both sides by k, right, of my differential equation. So I don't really need this k. I can get rid of its magnitude. All right, so r of x equals, it becomes x to the negative 2 times e to the negative x to the negative 1. Okay? All right, this becomes our integrating factor. And so now if we just jump straight to our solution, what is the solution for y? Is 1 over r of x integral qx rx dx. So let's plug things in. Rx becomes, well, it's 1 over, so this is negative, so this becomes x squared e to the x to the negative 1, right? Times this integral, what was qx now? I forgot. Let's go back up to the top. It's just 1. Okay, so we don't have to do anything there. So now we're just doing 1 times this integral. So it's x to the negative 2, e to the negative x to the negative 1. Okay, this is the general solution. Okay, and so what can we do here? What can we do here? How are we going to solve this integral? It may look complicated, but it's actually not all that complicated. Look, we've got something that, so negative x to the negative 1 looks like it is the derivative, right? It's some multiple of the derivative of x to the negative 2. Okay, so let's choose, if we choose, okay, see this guy, actually the other way around. If you take the derivative of x to the negative 1, x to the exponent negative 1, okay, you get x to the negative 2. So look, let u equal, okay, negative x to the negative 1. So du by dx equals x. So we multiply by the negative 1, and then negative 1 minus 1 is negative 2. So that du is equal to, so multiply both sides by dx, is just x to the negative 2 dx. Okay, so now we're going to do some subbing in. Okay, so if du is this x to the negative 2, and we have dx here, then we just have e to the u, right? So this guy becomes, okay, let's put the x squared in here. X to the negative 1 times, now we have the integral of e to the u. Okay, that's this guy. Okay, and then x to the negative 2 dx becomes du, which we get from here. And so the integral of e to the u du is just e to the u plus c. So let's get the x squared, e x to the negative 1, and then this becomes e to the u plus some constant. And we'll sub the u back in. U is x to the negative 1. So this becomes x squared e times x to the negative 1 times e. This becomes negative x to the negative 1, okay, plus c. So really, if I keep the c, right, I can start multiplying things out, or I can leave things as they are. This is y, right? This is y. So what we have x squared. Okay, this e x to the negative 1 times e negative x to the negative 1, they cancel, right? So it just becomes x squared plus, now c, and then just x squared e x to the negative 1. Okay, we're now going to take a look at another example of something we can solve using the integrating factor method. So let's look at problem D. Okay, so in this example, we have dy plus y times 3 dx equals e to the negative 3x dx. Okay, so if we compare, this is dy by dx plus p of xy equals q of x. Okay, what that means is what we need to do is divide everything by dx. And what we get is dy dx plus 3y equals e to the negative 3x. These cancel. So we have p at x is 3, q of x is e to the negative 3x. So here, our first step is our first equation is to find the integrating factor r of x. And that is e to the integral of p of x dx. Okay, which in this case is e to the integral of 3 dx, which is just e to the 3x. Okay, so now that we've got the form, we've found the integrating factor r of x using p of x, and now we can find the exact solution. So y is equal to 1 over r q r dx. So let's sub it in, let's find it. So y is equal to 1 over e. Actually, we could just say 1 over e to the 3x is e to the negative 3x. Okay. Q is e to the 3 to the negative 3x. And r is e to the 3x dx. So these cancel, and what we get is e to the 3x. This is just x plus some constant. And that's it. We've solved our differential equation. Okay. So this is the solution to that differential equation. All right, let's do another example. I'm going to leave this one there. And we'll call this example E. Okay. And in this example, our differential equation is 3x dy minus y dx equals 9x dx. And again, the form we want to convert it to is dy dx. Just clean that up a little bit. Dy dx plus p of x y equals q of x. So if we want, what we do, divide both sides by 3x dx, right? Because we want dy dx. We want this to cancel. Okay, and so this is also 3x dx. Okay, so divide both sides by 3x dx. This whole thing becomes 3. Okay, so let me rewrite it. So it's dy by dx. Okay, is so it's minus 1, 3, and this is x to the negative 1. Okay, oh, I forgot the dx here. That's going to cancel out. Okay, and that equals, oh, there's a y here, so that's y, and this equals 3. So this right here is p of x, that's q of x. Okay, so we need to solve for, first thing is r of x is equal to e to the integral px dx. Well, what's that? Well, that's e. We have the negative 1/3. Let's pull that out from px. And then we just have 1 over x dx. So this guy becomes e to the negative 1 over 3. Okay, and then we're going to have a ln x plus really some constant, right? This is an indefinite integral. Now this constant, okay, this constant is basically, if I draw it out again, it's called the C naught. This right here is just a constant, okay? So really that's just C e to the 1/3 ln of x. But you see r gets multiplied by both sides of the equation. So this constant will be canceled out. Okay, you can divide both sides by that. So what we're left with is this guy right here. So we need to simplify this a little bit. Just to show you here, ln, we'll just say a ln of b is the same thing as ln of b to the a. So we need to take that over here. Okay, so really that's the same thing as e. Now I forgot the negative here, so I should make sure to keep that. This becomes e, so the ln of x to the -1/3. Okay, now what is this evaluate to? Well, ln is base e, and ln of x to the -1/3 is equal to something. I put this empty box here. So this e to the exponent of this box is x to the -1/3. So look, this e is to the same box. So that means that this is x to the -1/3. Okay, so this is the r of x. Now, one thing that I forgot to mention, this c that we canceled out, okay, here, let me uncancel it for a second. Okay, this c that we would have on both sides can be both positive or negative. So when we cancel, we can just divide out the magnitude. And being positive or negative really means that we don't really care about this absolute value, because the c will make it r of x positive or negative. So it's not going to be only positive value. It can be all of the above. So we're saying that the integrating factor is x to the -1/3. Okay, so that's good. I'm just going to make some space here, get rid of this. All right, so we're going to go from our differential equation. Now that we have r, okay, the integrating factor, we can go straight to the solution. Okay, q and r are both functions of x. So we're going to say, so r is x to the -1/3, so this becomes x to the 1/3, so 1/r is that. And then q, we said was 3, so I'm going to take the 3 out. And then we have x to the -1/3 dx. Okay, so now we just have to integrate the -1/3, right? So let's do that. So this becomes 3x to the 1/3. And what's the integral? So it becomes x to the -1/3. We add 1, and then we divide by -1/3 plus 1. And we have an indefinite integral. So there is a constant of integration. Okay, let's draw a line over here. Okay, so let's evaluate all of this. So we have 3x to the 1/3, okay, times, so it's x, -1/3 plus 1 is 2/3. So we're divide by 2/3, right? Whenever you divide by 2, that's like multiplying by 3/2, and we add c. Okay, let's multiply everything through. Okay, so 3 by 3 is 9. X to the 1/3 times x to the 2/3. It's like 1/3 plus 2/3. That's just x to the 1, right? And now we have the 2. And then the c just gets multiplied. So it becomes 3c, right? X to the 1/3. This can just be another constant. We could just call this c naught if we like. So in summary, it becomes 9 over 2 x plus c naught x to the 1/3. Okay? And that's what y equals. So this becomes our solution to that differential equation. All right, let's do another one. So where are we here? We're on example E. Let's do another one. We'll call it example F. Okay. Zoom out a little bit. Okay. So we'll call this example F. So what is this one going to be? All right. Let's do a simple example here. Let's go. So dy by dx, okay, minus 2y equals 2e to the 2x. So it's already in the form dy by dx plus p of x, y equals q of x. This is the form that we can solve. And so we can identify, here's p of x, here's q. Okay, and so what we need is we need r. Okay, so let's do that. So what's r? Well, that's pretty simple here. Becomes e to the negative 2 dx. So this becomes e to the negative 2x. So we have the integrating factor, and now we have to jump. We can jump to the solution. Y is 1 over r, okay, qx rx dx, okay? Say 1 over r of x. Sometimes I forget to put that it's a function, but it's understood that it's a function. Okay, so now let's plug things in. So 1 over e to the negative 2x is just e to the 2x. Okay, and then what we have is we have the integral qx. So I'll bring the 2 over here. So it becomes e to the 2x, so that's qx, times rx is e to the negative 2x dx. And so these two cancel, and I just have integral of dx, which it's an indefinite integral, becomes x plus c. And that is all. Let me see. Let's make sure we're clear. Yep. Yep. Okay. So that's it. That's basically how it is. Okay. All right. Okay. So this is our solution to our differential equation. Let's look at one that's a little harder to solve. Okay. So this one right here is going to be, we have dy by dx plus 2y equals sine of x. So here, again, dy dx plus p of x, right, y equals q of x. So here's p of x, here's q of x. Okay, so our integrating factor okay, so our integrating factor is e to the 2x. And so when we go and we say, okay, now I'm going to solve directly. This integral is going to be a little more difficult to solve. Okay, so it's e to the negative 2x times, now we have this integral. The integral qx is sine x. So we have, e to the 2x, right? That's the rx. And then sine of x dx. Okay, so here we are. We have to solve this, this integral. Now this integral has a sinusoid in it, and we can't do a u substitution here because e to the 2x and sine x, there is no derivative relationship between the two. Okay, so this really looks like, okay, we need to do an integration by parts to solve this. And oftentimes, whenever you have a sinusoid in an integration by parts, you often have to do it twice. Okay, so what I'm going to do is I'm going to take this guy right here. I'm going to rewrite it. So we're going to say, sorry, it's going to say integral. So we're just going to solve that. And then once we solve this guy, okay, then we'll sub it in for y. So what is e to the 2x sine x dx? What is that? What's it equal to? So look, we're going to do an integration by parts here. So what is integration by parts? The integral of u dv equals u v minus the integral v du. Okay, so when we do this, we have to choose, okay, what is u and what is v. And oftentimes, what we have to do here is we have to choose u to be one of the sinusoids. So in this case, we're going to say u is sine of x du, okay, must therefore be e to the 2x dx. Okay. Oh, whoops. Sorry, that's dv. I have to see what we have. Sorry. This is dv. dv is, so u has to come from our integral. dv has to also come from our integral. I'm sorry. dv. Put it in the wrong column here. 2x dx. So du, what's the derivative of sine? So du dx, du dx would be cos x. So if I multiply both sides by dx, then I have cos x dx. And if dv is e to the 2x, right? If dv is e to the 2x, what's the integral of that? Well, that means that v is the integral of that. Well, let me go up here. The integral of e to the a, or actually we should say e to the ax dx is equal to 1 over a e to the ax, okay, plus c because of the indeterminate. It's an indeterminate integral. So this becomes 1 over 2 e to the 2x. Okay? That becomes the integral. Okay. So now we're going to sub everything in. Okay, we're going to sub these guys. We got the uv, and then we got the v du. Okay, so let's do that. Okay, let's do that over here. So we'll say, I want to put it all on one line here. Let me move this down. Let's just draw a line over here. Okay, equals, so uv, so that is sine x, we'll do the 1/2 e to the 2x, okay, minus the integral, and here's where we get our v du. Okay, there's the 1/2 here, e to the 2x du is cos x dx. Okay, so here we haven't found anything yet, but we now have another integral here to contend with, and we need to do an integration by parts in order to solve this integral. So what I'm going to do is I'm going to move this over, and we need to do a second integration by parts. So we now, like we did before, we're going to choose u is the sinusoid. So we're going to say here it's cos of x. So if we take the derivative of that, du by dx is negative sine of x. If I multiply both sides by dx, I can do this. Okay, so what we're saying is that this guy's u, and dv is e to the 2x dx, as up here from our formula. Okay, so what is, see, we need v du. So what is dv? So dv, in this case, okay, if cos x is u, then dv, what's left is e to the 2x dx. So if you integrate that, you get 1 over 2, right? E to the 2x. This is the same as what we had up here. Same thing we had here. Okay, so dv is exactly the same. So now we can say we have uv, right, minus v du. So this guy right here, we can replace. Okay, so let's do that. Let's write everything out again. So, oops, I touched the wrong spot. Okay, e to the 2x sine x dx equals 1/2 sine x e to the 2x. Okay, and now I'm going to put a minus 1/2, and I'm going to plug in the formula, right? It's uv minus v du. What's uv? Well, uv is, okay, it's 1/2 e to the 2x times cos x minus, now we have the integral of v du. So v is 1/2 e to the 2x. Du is negative sine x. So I'm going to put a plus here. Sine x dx. Okay. All right, so we did that. But what you'll notice here, look what you notice. We have e to the 2x sine x dx. E to the 2x sine x dx, but 1/2. Okay, but we haven't multiplied everything through, so we should. So what we need I'm going to write this out again. E to the 2x sine x dx equals 1/2 sine x e to the 2x minus 1/4 e to the 2x cos x, right? Minus 1/4 integral e to the 2x sine x. Oops, I should put a dx underneath. Too high. Let's put it over here. Okay, so what you notice is I can take this guy and bring him over to the other side of the equation. So this is like 1/1, right? Or 4/4, let's say. And this is 1/4. So really, if I bring this guy over to the left-hand side, what I get is I get 5/4, right? Integral e to the 2x sine x dx equals, okay, equal to 1/2 sine of x e to the 2x. Actually, let me do this. Let's pull out the 1/2 e to the 2x from these guys. So I'll say 1/2 e to the 2x, okay, and then pull out sine of x, and then here minus just 1/2 cos x. Okay, so now what I'm looking for is what is e to the 2x sine x, right? If I go up here, I want the integral of e to the 2x sine x dx. That's what I want, because I'm going to replace that here. You see this star here. Replace this, and then I'll know why, because it's just going to be, y is just going to be e to the negative 2x times this integral. And I'm about to solve that integral right here. So if I multiply both sides by 4/5, okay, or I just multiply, yeah, so this becomes, if I multiply this side by, so it's e to the 2x sine x dx. So I've multiplied the left-hand side by 4/5, so I got to do the same thing here. I got to say 4/5 times, right, this 1/2 e to the 2x sine x minus 1/2 cos x. I know I'm taking a lot of steps. I didn't really need to, but take this out. This becomes a 2. But what I'm going to do, I'm going to multiply. So that this 2 that I have here, I'm going to put it inside the, so I'm going to say 2 here, and 2 here. So this 2 is gone. So this becomes 2 sine x. I'll put this minus cos x. So at the end of the day, integral e to the 2x sine x dx is 1/5, or we just say e to the 2x over 5. Okay? 2 sine x minus cos x. Hey, we can sub this guy, actually sub this where the star is. So e to the 2x over 5, 2 sine. So here, look, let me rewrite it. It's right here. This is y. Okay, so now I know y. So really all I got to do is take what I just solved, star, multiply by e to the negative 2x. Okay? So y becomes, let me rewrite it as e to the negative 2x times this integral. Right? And this is what we wanted to solve. So I'm going to sub in what I have here into here. So y is equal to e to the negative 2x times e to the 2x over 5, 2 sine x minus cos x. So they cancel. So y equals 1 over 5, 2 sine x minus cos x. This is the solution to the differential equation. Okay. And that's it. So that's it for today. I hope you enjoyed this video. I hope you enjoy all my videos, and I will see you next time in math class. All right.